we continue our discussion on forecasting models. In the last lecture, we developed forecasting models for this data. This data we assumed represented a constant model, and we looked at forecasting models for this data. We looked at simple average, weighted average, moving averages and simple exponential smoothing, and all of them we used to test on this model. In this model we assumed that this data represents a constant and we were trying to find out that constant. The fact that each of these data does not represent the constant comes from our belief that there is an inherent variation or noise or something which cannot be assigned to a specific cause or a specific reason. Therefore, we assumed that this represents a constant and we tried to fit a model that gives us that constant. Now, today we will look at a different type of data and we will move to this data. Now, if we look at this data and if we ask anyone to forecast this data, we will end up giving a forecast which is greater than 35, because as we move along these numbers, we realize that there is an increasing trend. So, we use the term trend to show a certain behavior, and in this case there is an increase. Now, we will not and should not fit a constant model for this data. For example, if we took the simple average, then the simple average, the total of these 6 numbers happens to be 181 and the simple average will be 30.16. Now, simple average 30.16 is always within the range of values and therefore will be somewhere here, while a meaningful forecast would be a number which is more than this 35. So, we do not use the earlier models directly, we do not use models like simple average, moving average, simple exponential smoothing, etc. directly to give the forecast for this. So, we have to now build different forecasting models that are capable of capturing the trend which this data is exhibiting. So, let us first look at a very simple model that captures trend, and then we will look at a more advanced model that can capture trend. Now, before we move to any model, let us try and plot these with respect to time. So, let us call this as time equal to 1, time equal to 2, time equal to 3, 4, 5 and 6. Let us plot this with time on the x axis and the data on the y axis. So, let us plot here time and then here we have D, which is the demand or sale for this particular product. So, at time equal to 1, 2, 3, 4, 5 and 6, and let us say the values we start here from 24, 26, 28, 30, 32, 34, 36 and so on. So, at t equal to 1 the value is 26, which is here, t equal to 2 the value is 28, which is here, t equal to 3 the value is 29, which is here, t equal to 4 the value is 31, which is somewhere here, t equal to 5 the value is 32, which is somewhere here, and t equal to 6 the value is 35, which is somewhere here. So, this is how the 6 points are plotted when you plot them on this, and one look at these 6 points kind of conveys to us that there is an increasing trend, and they in some sense if we try to draw a line, the line will go like this. Now then when we try and draw the line, we ask ourselves a couple of questions. Are we going to draw a line? Obviously all these 6 points are not collinear. So are we going to draw a line which is going to pass through maximum number of points, or are we going to draw a line which kind of best represents the 6 points by being as close to each of these 6 points as possible? So the answer is we do the second, and we then try and fit a line or draw a line which is as close to the 6 points as possible. So let me first draw the line using a free hand and then explain a few things. Let us assume that this line is going to be like this. Now if we draw this line, then what we are going to do is, now this point is represented by this point on the line. Say this point is represented by this point, this is represented by this point, this is represented by this point, this is represented by this point, and this is represented by this point. Now right now, though I have drawn this line, I do not know the equation corresponding to this line because I have made a freehand sketch. So I would like to now find the equation corresponding to this line. One of the ways to do that is by, if we consider a point like this, this point is going to be represented by this point on the line, and therefore there is going to be some kind of a gap between the actual point and the point which is there on this line, and let us say we call this gap as the error. We call this as the error. Now if we want this line to be as close to these 6 points as possible, then we will have to draw the line in such a manner that the errors are as small as possible. The moment we define that the errors have to be as small as possible, we also have to observe that in some situations the error can be positive, while in some other situation the error can be negative in the other direction. So we obviously do not want these positives and negatives to cancel out each other. Therefore a better way to look at it is to say that we want to draw this line in such a manner that the squares of these errors are minimized, or essentially we try to minimize what is called the error sum of squares. Try to minimize the error sum of squares, which is essentially we try to minimize E square, where E is the error corresponding to each point. So there will be 6 points here, there will be 6 error terms. Now we want the sum of the squares of these 6 errors to be minimized. Or if this line is going to have coordinates a plus bt, where a and b are to be determined, then the error term will be y minus a minus bt is the error term. Error term specific to a particular point, say the tth point, can be written as Et is equal to Yt minus a minus bt. Now sum of squares of these errors will become sigma Et square is equal to sigma Yt minus a minus bt square. Now we want to minimize the error sum of square. So we minimize error sum of squares, which gives us minimizing Yt minus a minus bt the whole square. Now we want to find out the a and b, which represents, b represents the slope and A represents the y ordinate or the value on the y axis for t equal to 0. So, A and B have to be found out such that this error sum of squares is minimized. Now, let us try and derive a very simple expression to find out A and B. So, we want to minimize y minus A minus bt square. Here I have represented it as yt minus A minus bt. Here I am writing it as y minus A minus bt. We could also write it as yt minus A minus bt. Now, this has to be minimized and A and B have to be found out. So, the condition for minimization is the first derivative equal to 0 with respect to the variables. So, we try to partially differentiate this with respect to A and then with respect to B and then try and get the values. So, partially differentiating with respect to A, we would get 2 times y minus A minus bt with a minus sign summation. So, summation equal to 0, and partially differentiating with respect to B, we would get sigma 2 times y minus A minus bt into minus t is equal to 0. Observe that when you differentiate with respect to B, so it becomes 2 times y minus A minus bt, and then differentiating with respect to B, so we get a minus t. So, the minus is written here and the t is written here. Now, we expand this summation and we therefore write 2 equations. The minus becomes irrelevant here because the right hand side is 0. So, we get an expression sigma y is equal to Na plus B sigma t. This goes, the 2 also goes. So, sigma y is here, you take it to the other side. So, sigma A is n times A, where n is a number of data points. So, Na plus B sigma t, B is a constant that can be taken outside. So, B sigma t is the first equation. Second equation will be sigma yt is equal to A sigma t plus B sigma t square. Now, multiply here. So, yt, again this minus and this 2 goes. So, you have yt is equal to A sigma t and then plus B sigma t square comes because this t is multiplied by the other t. So, you have 2 equations and 2 unknowns A and B, and we can directly solve using these. Now, there are times it is also possible to simplify this to write unique expressions for A and B, but right now we are not going to do that. We are going to keep these equations as they are and we are going to solve. Now, if we consider this data 26, 28, 29, 31, 32, 35. So, we look at this data 26, 28, 29, 31, 32, 35. This is your yt or y as you may call. So, this is y1, y2, y3, y4, y5 and y6. We need sigma y or sigma yt is a sum of all of them, which is 181. 14, 23, 24, 26, 31, 181. So, this term we have written. We need B sigma t. So, t is 1, 2, 3, 4, 5, 6. So, this is 21, 3 plus 3, 6 plus 4, 10, 15 plus 6, 21. So, we have this term B sigma t. Then we need a term for sigma yt. So, you need a yt term. So, y into t. So, 26 into 1 is 26, 28 into 2 is 56, 29 into 3 is 87, 31 into 4 is 124, 32 into 5 is 160, 35 into 6 is 210. and the sum is 12, 19, 23, 2, 3, 9, 11, 19, 24, 26, 4, 5, 6, 23, 2, 9, 19, 24, 26, 2, 3, 4, 663. And then we have now found out this term sigma yt. Now we need to find out this term, which is sigma t square. So we write t square as 1, 4, 9, 16, 25 and 36. So this total will be 5 plus 9, 14, 30, 55, 91, 71, 61, 77, 86, 91. So now these two simultaneous equations become sigma y 181 is equal to Na 6a plus b sigma t 21b, and 663 is equal to a sigma t 21a plus 91b. So we have two equations with two unknowns, and we need to solve these two for a and b. So the easiest thing to do is to multiply this by 2 and multiply this by 7, so that we can cancel the a and then get the value for b, and then we go and substitute to try and get the value for a. So when we solve this, we get the solution a equal to 24.2667 and b is equal to 1.6857. This means that this line is going to intersect the y axis at a value of 24.2667, and this line of best fit has a slope of 1.6857. But then we are interested in finding the forecast for the 7th period, which actually led us to drawing a line and finding out the coordinates of that line. So now for the 7th period, the forecast that we are going to make is the point corresponding to t equal to 7 on this line, which is this point, is what we are interested as the forecast for the 7th period, and that is given by a plus 7b. So F7 forecast for the 7th period is a plus 7b, which is 24.2667 into 7 times 1.6857, which is 36.066. So this is our forecast for the period number 7, and let us say this is going to come at 36.066, which is the forecast for period 7. So the model that we have just now seen is the linear regression model. The linear regression model, which also gives us the line of best fit given these set of points. Now the forecast for the 8th period can be given by F8 is equal to a plus 8b and so on. Now this method is a very intuitive, nice method to try and forecast when the data shows a certain amount of trend. Now let us go back and look at this method again. What have we done, or what are the assumptions behind this method of linear regression for time series data with trend? what are the assumptions. Now, first thing we have done is we have considered all the data points. Second is we have given equal weightage to all the data points. Even though we squared the error and tried to minimize, we did not associate a weight with each of these. For example, we did not do minimize Wt into y minus a minus bt the whole square. We did not do that, which means that we have given equal weightage to all the data points. And third is we have tried to minimize the error sum of squares. Now, let us go back a little bit and try to see whether we use the same assumptions in any of the models for the constant data that we had here. Now, for example, if we make the same three assumptions on this, which means we fit a model which uses all the data points, which fit a model which gives same weight to all the data points, and we try and fit a model which minimizes the error sum of squares, except that because this data is constant data, we fit simply y equal to c, and because this data shows trend, we fit y is equal to a plus bt. Now, suppose we do this, then we fit y equal to c, and then we minimize the error sum of squares. So, error sum of squares will be sigma y minus c the whole square, and if you want to find out c such that y minus c the whole square is minimized, then the answer for c will be simply sigma y by n, which is the simple arithmetic mean. So, if we try to fit a model y equal to c using linear regression and minimizing error sum of squares for a constant data, we get the simple arithmetic mean. When we make the same assumption that we want to consider all the data points, equal weightage to all the data points, and minimizing the error sum of squares, considering trend and fitting a plus bt, we get this linear regression model. When we were looking at this set of data, the constant data, we also said that even though it is a good idea to use all the data points, we would rather give a little more weightage to the recent points and little less weightage to the older points. And that thinking of ours led us towards moving averages and particularly towards exponential smoothing, which we saw in the previous lecture. So, if we were convinced that exponential smoothing is a very good model to do forecasting for this type of data, then the obvious question is, can we have models based on exponential smoothing to do this data with trend? We also know that simple exponential smoothing that was used here was very effective, but simple exponential smoothing would only give us a forecast which is within the range, just as simple average gives us a forecast which is within the range. So, simple exponential smoothing obviously will not work here, and simple exponential smoothing will actually lag behind the last value. It will give you a value closer to the mean, which means it will lag behind the last value. So, we need a model which uses ideas from exponential smoothing, at the same time gives different weights to different data points with more weightage to the recent points and lesser weightage to the old points. We will now discuss the Holt's model, which does exactly that. It considers all the data points, it uses ideas from exponential smoothing, and it gives progressively more weights towards recent points. In the Holt's model, we fit ft plus 1 is equal to at plus bt. Now, f t plus 1 is the forecast for period t plus 1, a t is called the level which represents the smoothed value up to and including the last data. B t is the slope of the line that we are fitting at the point t. So, a t is the representative value of the level or the constant, and then we add a slope to it, so that we get the forecast of the next period. So, forecast of the next period will be level at the end of the previous period or the present period, and then we add a slope to it. So, a t plus b t. Now, both a t and b t are updated for every data point using exponential smoothing. So, a t, which is the level value up to and including the last point, is given by alpha d t plus 1 minus alpha into a t minus 1 plus b t minus 1. Actually, this is our very familiar exponential smoothing equation. The normal exponential smoothing equation has two parts. One is the demand part and the other is the forecast part. Alpha d t plus 1 minus alpha f t. Now, alpha d t is the same, alpha is the weight, d t is the demand during the last period. 1 minus alpha, I had used f t in the last lecture, but I had also mentioned that there are two versions of it. So, now we will use a version alpha d t plus 1 minus alpha f t minus 1. So, f t minus 1, which is the forecast made at the end of period t minus 1 for period t. So, in some sense d t and f t minus 1 are comparable. F t minus 1 is the estimate of d t. In this notation, f t minus 1 would mean that it is the forecast made at the end of period t minus 1 for t. So, a t minus 1 plus b t minus 1 represents the forecast for period t, just as forecast for period t plus 1 is represented by a t plus b t. So, here the equation is like alpha d t plus 1 minus alpha f t minus 1, right. Alpha d t plus 1 minus alpha f t, where f t is for a t minus 1 plus b t minus 1. Forecast made for period t is a t minus 1 plus b t minus 1. Now, b t, which is the slope, also has two components. One is in some sense the component that comes out of the level, and the other is a component that comes out of the slope. So, beta is another exponential smoothing constant like alpha, beta into a t minus a t minus 1. If you take the present level value a t and take the previous level value a t minus 1, the difference between them in some sense represents a slope. So, that is one component of the beta, the b t. The other component comes from the actual slope that was computed. So, the b t also has two components that are related through exponential smoothing. The a t also has two components that are related through exponential smoothing. Now, let me explain this further. Now, when we did the y equal to a plus b t through linear regression, now these were the 6 points, the white dots are the points, and we tried to fit a line that passed through all of them and is as close to these 6 points as possible. In the Holt's model, we will not do that. For example, we are here at the 6th point and we are interested in forecasting the 7th point. Now, this white thing is your D6, the demand at the 6th point, which is the data that we know. the level value at t equal to 6 is the equivalent of this point, which is actually representing that. The level is obtained by through exponential smoothing. Considering these things in a certain manner, up to and including D6, we have a level which is here. So, once we know this level, plus we also need the slope at this point. In the linear regression model, after we fit the line, the slope is the same at every point in the line. In the Holt's model, we are going to kind of redefine the slope at every point up to and including the last point. So, we will do some calculations here to find the slope, and therefore, A6 plus B6 will give us F7. How do we find A6 and B6? Now, A6 and B6 have two components. Now, AT, now if you look at this, AT has a component alpha dt plus 1 minus alpha into AT minus 1 plus BT minus 1. So, AT has two components, one that comes out of this demand, the other that comes out of this. This is your AT minus 1 plus BT minus 1, this plus this. So, this is computed using this one and this plus the slope here, and they are related through an exponential smoothing equation. Similarly, the slope at this point also has two components. One is the slope at t minus 1, the slope at this point, and the other is essentially the slope between this point and this point, which comes from AT minus 1. So, in some sense, in the Holt's model, for every point t, we are actually trying to find out a level and a slope, and we add them so that we get the forecast for the next period. Then we know that forecast for the next period, and then we know that demand point, and keep iterating this till we get to the final answer. So, let us explain the computations in the Holt's model for the same set of data 26, 28, 29, 31, 32, 35. We have already seen that we get a forecast of 36.066. When we fit this line, F7 became 36.066. Let us see what happens when we fit it using the Holt's model. Now, the same data we are going to use 26, 28, 29, 31, 32, 35. Like in all exponential smoothing, we need some initial values, and we also need to fix the values of the smoothing constants. So, we fix alpha equal to 0.2. Note that alpha is the exponential smoothing constant when we compute AT, and beta is the exponential smoothing constant when we compute the slope. So, alpha is 0.2, beta is 0.3 is what we have assumed in our calculations. We also need some initial values. So, the very first value, which is 26, we assume D1 to be 26, D1 equal to A1 equal to 26. So, we assume that the level, the first point that we calculate here, this is 26. So, the white point represents D1 and the other color point represents A1. So, right now we are going to assume that the level value for the first point is the same, that is one of the assumptions, and we also need to initialize a slope here, and in order to do that we actually we know these 6 points. So, with the known 6 points, the initial slope is the approximate slope of the line joining the first point and the last point. So, the initial value of the slope is therefore 35 minus 26, which is 9 divided by 5, which is 1.8. So, the initial values of A1 and B1 are 26 and 1.8. So, from our equation for Holt's model, F2 is equal to A1 plus B1, which is 27.8. Now we need to find out A2 by our previous equation. AT is alpha dt plus 1 minus alpha AT minus 1 plus BT minus 1. So, A2 will be alpha D2 plus 1 minus alpha D1 plus 1 minus alpha into A1 plus B1. So, alpha D2 plus 1 minus alpha into A1 plus B1. 0.2 alpha is 0.2, D2 is 28 which comes from here, plus 0.8 into A1 plus B1 is what we calculated, which is F2. So, 0.8 into 27.8 which becomes 27.84. So, when we apply the Holt's model, this value is 28, the white one is 28 which is the demand point, and this one is 27.84 when we apply the Holt's model. So, we got 27.84 here. The slope at this point, is now calculated. The slope at this point was assumed to be 3, calculated to be 3. Here it is now calculated using exponential smoothing. So, the slope at this point is now beta into A2 minus A1 plus 1 minus beta into B1. So, beta is 0.3. A2 minus A1 is the difference between the computed 27.84 and 26, which is 1.84, plus 1 minus beta is 0.7 into the previous slope, which is 1.8. So, it now becomes 1.812, and F3 is A2 plus B2, which is 29.652. Now, D3 was 29 and F3 is 29.652. Now, we need to find out F4. To find out F4, we need A3 plus B3. Now, A3 and B3 have to be calculated using these. So, we can now progressively calculate the rest of the numbers, and this table explains what these numbers are. So, for period 4, D4 is 31, A4 is 31.2352, B4 is 1.755, and this is 31.294, and if we move on, we find out finally that F7 is 36.32. So, let me write this 36.32 here. This is using the Holt's model. This is from the Holt's model. Now, in the Holt's model, if we look at this, finally A6 is 34.592, B6 is 1.7272. So, A6 is here, the representative value was 34.592, B6 was 1.7272, and finally we got 36.32. So, the representative value here was 34.592, the actual value is 35. The slope is about 1.8, but the slope has come down to 1.7272, and the final value is 36.32. Now, we observe that the forecast given by Holt's model is slightly higher than the forecast that we got using the linear regression. Now, it is not absolutely necessary that every time the Holt's model will be slightly higher than linear regression, but it is very likely so. One of the reasons is, if we look at this data, the value keeps increasing, but then if we look at the last few numbers, the increase is slightly higher than what it was before. So, when we fitted the line, we gave equal importance to all these points, and therefore, the smaller increase essentially pulled it back a little bit, and we got 36.066. Now, because we are giving higher weightage, the 35 which shows a larger increase is tending to pull it slightly towards this 35, and therefore, the value became slightly more than this. But one of the advantages of Holt's method is that it captures idea of exponential smoothing, which means we are giving more weight to the more recent point while doing the forecast, and in some sense we are actually calculating the level and the trend, the forecast at every point through an iterative process that involves exponential smoothing, unlike linear regression where we compute it in one shot by giving equal importance to all the points. So, in some sense what simple exponential smoothing did to this data, Holt's method tries to do to this type of data. So, this is how we normally forecast when the data exhibits trend. We will now see one more aspect of forecasting. So, let us assume that we are looking at this kind of a data where the year is divided into 4 quarters and the data is given for each quarter for the 3 years. So, if we take year 1, the quarterly data are 53, 22, 37 and 45. Now, when we start looking at this table, we observe that there seems to be a trend in this direction for all of them. The total also seems to go up, but each quarter of the year is not showing constant kind of data. There is a variation in this. Now, this thing is called seasonality. So, each quarter represents a season and the data is showing a certain seasonality in this case. So, we need forecasting models that capture seasonality. Seasonality is important because several products exhibit seasonality. Common examples that are given are the sale of ice creams are higher in summer than in winter. The sale of air conditioners is higher during summer than during winter. The sale of, in some places, the sale of heaters is higher in winter than in summer. Sale of sweaters are meant to be higher in winter than in summer, and so on. So, products exhibit a certain seasonality. And now, can we capture that seasonality of the product and then make the forecasting is the next question. So, we will first build a simple seasonality model and then we will also develop or explain a seasonality model that uses ideas from exponential smoothing. So, the simple seasonality model is like this. First, let us find out the total demand for the 4 years, and this is 157, 173, 1 189, 189. So, these are the total demands in the previous years. Now, what we do is we try to associate a seasonality index with every season. So, seasonality index associated with the first quarter is the proportion of the total demand met by the first quarter. So, that will be 53 divided by 157. So, 22 divided by 157, 37 divided by 157 and 45 divided by 157. Now, again seasonality index in the second year will be 58 divided by 173, 25 divided by 173 and so on. So, we compute the seasonality indices for the 3 years and for the 4 quarters. So, the seasonality indices are so these 4, 53 divided by 157 is 0.34, 22 divided by 157 is 0.14 and so on. So, the seasonality indices are calculated this way. Now, from these seasonality indices we can, all these will have to add up to 1, and from these seasonality indices we can find out the average of the seasonality indices. So, the average of the seasonality indices are given here 0.337, 0.14, 0.233 and 0.293. These are averaged across this way. Now, some of the averages also has to be equal to 1, but sometimes there could be some rounding off errors in the average, and therefore, this may be slightly less than 1 or it may be slightly more than 1, but many times it is exactly, it will add up to 1. If it does not, we can normalize it to 1, so that the sum of the indices is also 1. So, now we have captured these indices, and based on this average over 3 years we can say that quarter 1 accounts for 33.7% of the total demand on an average, quarter 2 accounts for 14% of the total demand, quarter 3 accounts for 23.3% of the total demand, and quarter 4 accounts for 29.3% of the total demand. Now, the totals are 157, 173, 189, and the totals show a certain increasing trend or a linear trend. Now, we can fit a model to forecast the demand for the 4th year. Now, for this particular example there are only 3 data points. So, it will be difficult for us to fit an exponential smoothing based model or a Holt's model. So, we rather go for linear regression, and then we can fit a model of the type y is equal to a plus bt. So, when we fit a model of the type y is equal to a plus bt, we get y is equal to 141 plus 16 t, and the forecast of the demand for the 4th period at t equal to 4 will become 205. So, 205 will be the forecast of the demand for this period, and since we know that quarter 1 accounts for 33.7% of 205, quarter 2 accounts for 14% of 205, we simply multiply by the proportions to get the 4 forecasted values, which are 69.08, 28.7, 47.77 and 60.06 are the forecasted values for the 4 seasons. So, 62 next forecast is 69.08, 27, 28.7 and so on. So, this is a very rudimentary algorithm to do seasonal forecasting, where we de-seasonalize the data, compute the seasonality indices, average the seasonality indices, separately take the total demands, forecast the demand and multiply by the seasonality indices to get the new forecast for all the 4 seasons. There are only a couple of questions in this rudimentary algorithm or method, and we will see that today before we close this lecture. First question that is commonly asked is, why cannot I take only these 3 values and independently fit a y equal to a plus bt and get the forecast? Mathematically it is possible and it is doable. If you do that, you will even get a value which is very close to 69.08. Normally that is not done because it means 2 things. It means you are treating this quarter as independent of the other 3 quarters, whereas when you fit a seasonality model, you are capturing somewhere the dependency between or amongst the quarters. So, you do not do this independently. It is also equivalent of saying there are 12 data points, I am picking up data point number 1, 5 and 9 and I am trying to forecast the 13th data point, which is not normally done. So, we do not normally do that, we de-seasonalize it and then we bring it back. Second question that is often asked is, now what if this itself shows a trend 29 to 29 and 30, should I average this or should I fit another trend model right here, assuming that there is an increasing trend? The normal answer is you average it, unless you really have several years of data to show that in a particular quarter there is the index itself is showing a trend. If the index itself is showing a trend and if you are convinced, you can fit a trend model there, which also means that if one index is showing an increasing trend, somewhere else in some other quarter it will show a decreasing trend, but ordinarily the average is taken de-seasonalized. So, the next model, which is called the Winters model, where we try and capture the level, the trend and the seasonality index using exponential smoothing, we will see in the next lecture.